we will now further our understanding of the derivative. Recall, the derivative of the function f of x at x equals a is written as f prime of a, and it is the limit as delta x goes to 0 of f of a plus delta x minus f of a all over delta x. So for each input value of x, we can compute an output value of f prime of x using the definition above. Now let's recall the definition of a function. A function is a mathematical rule which assigns to each input value an output value, just as we have here with our derivative. So the derivative f prime of x is a function itself, and we write it as f prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. Notice that it's the same definition as we have above, except we've used the variable x rather than the point a. So using this definition of the derivative of f of x, let's compute the derivative of the function f of x equals x squared. Recall that we did this at a single point before. Using our definition, f prime of x equals the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. And since the function f of x squares its input, f of x plus delta x is x plus delta x squared, and f of x is simply x squared. To simplify this, we need to multiply out x plus delta x squared. When we do this, we get x squared plus 2x delta x plus delta x squared. But now our numerator has both x squared and minus x squared. So these cancel each other out, and we're left with the limit as delta x goes to 0 of 2x delta x plus delta x squared all over delta x. But we can reduce this fraction because the top is divisible by delta x as well as the bottom. Doing this, up top we're left with 2x plus delta x. So in total we have the limit as delta x goes to 0 of 2x plus delta x. But as we make delta x smaller and smaller and smaller and closer to 0, this just becomes 2x. So we found that f prime of x equals 2x. F prime of x equals 2x agrees with what we computed earlier. Using our old-fashioned methods, we found that f prime of 1 equals 2. But it took us a while to get it. Now we can compute f prime of 0 and f prime of negative 1 very quickly by simply evaluating the function 2x. So f prime of 0 is 0 and f prime of negative 1 is negative 2. Since we did all the hard work in the last slide, it is now very easy to compute. Coming up in Chapter 3, we will compute the derivative of all the functions that we've talked about in this manner. Since the derivative f prime of x is a function, we can graph y equals f prime of x, and it will give us a better understanding of the derivative. Let's look at our last example. For the function f of x equals x squared, we have the following graph. Now with this, we want to look at the graph of the derivative, which is f prime of x equals 2x. Remember that the derivative at a point gives the slope of the original function at that point. On the left-hand side of the graph f of x equals x squared, we have a negative slope, so the derivative must be negative. As we move to the right, the derivative and the slope become less and less negative until it reaches a point where it's 0. After that, as we move further to the right, our slope is increasing more and more positively, as does our derivative. We will use this relationship between the original function and its derivative repeatedly throughout this course. Again, when the function is decreasing, the derivative is negative, and when the function is increasing, the derivative is positive. Previously, we said that a function y equals f of x is increasing if the average rate of change, delta y over delta x, is positive, and that a function is decreasing if the average rate of change, delta y over delta x, is negative. But now we have a new way of talking about rate of change. Now we say that a derivative y equals f of x is increasing if the derivative dy dx is positive, and a function is decreasing if the derivative dy dx is negative. And if the derivative is neither positive nor negative, then it must be 0. In this case, we say that a function is constant, meaning it's not changing if its rate of change is 0. Let's use what we just found to graph the derivative of another function. Here, we'll look at a function that we don't know the equation of, and we only have the graph. Using it, we want to plot the graph of f prime of x. With this function, our slopes start out positive, and so does our derivative. As our slopes decrease, the derivative does also, until the point where the derivative and the slope are both 0, after which our slopes become more and more negative until we reach the point where we have a negative slope, but it becomes less negative, all the way till we turn around and become positive again. Since the slope becomes positive, so does the derivative. As we move along the curve, we can see the relationship between the tangent line in our graph of f of x and the point on the curve f prime of x. Again, anywhere that the derivative is negative, our function is decreasing. And anywhere that our derivative is positive, our function f of x is increasing. Understanding the relationship between f of x and f prime of x is going to be our main focus for much of the rest of the course. So let's go over this one more time. When our function is increasing, the derivative is positive. Here we are increasing, but at a slower and slower rate until we start to decrease. At this point, the derivative becomes negative, and it remains negative until we reach the point where our function begins to increase again. After this point, the function is increasing, so the derivative is positive. In this case, it's increasing at a faster and faster rate, so the derivative is becoming more and more positive. Again, understanding the relationship between f of x and f prime of x is going to be essential for the rest of the course. As we look at this graph, we see two interesting points on the graph of f of x, the yellow point and the blue point. Looking at f prime of x, we notice that it lines up with interesting points there as well. We will study this very soon.